There is a class of Linux performance problems where nothing is technically broken. The GPU works, the NIC works, the CPU works, the workload runs. It is just slower than it should be. This is where topology starts to matter. On a big GPU server, devices are not all equally close to each other. A GPU might be attached to one CPU socket, a ConnectX adapter might be attached to the other socket, memory might be allocated on the wrong NUMA node, and suddenly traffic that should stay local is crossing an inner socket link every time data moves between the GPU and the network. The system still works. You just paid for a lot of hardware so it could take the scenic route. The first command I usually reach for is nvidia-smi topo m. That gives you a very fast view of how the GPUs relate to each other, the CPUs and the NICs NVIDIA can see. You will see labels like PIX, PXB, PHB, Node, and SYS. Those labels are telling you how many bridges or host boundaries sit between devices. The exact topology depends on the platform, but the idea is simple. Closer is usually better. Then I look at the Linux PCIe Express tree with lspci TV. This is where you can see which devices hang off which root ports and bridges. If I am trying to match a ConnectX adapter to a GPU, I want to know whether they are under the same root complex or whether the path crosses CPUs. Next is NUMA. numactl H shows the NUMA nodes, CPUs, memory, and distance information. Linux will also expose the NUMA node for a PCI device under sysfs. That makes it possible to build a simple map. GPU 0 is near this CPU socket, MLX50 is on that NUMA node, MLX53 is on this one. Now you can start asking whether the software is using sensible pairings. This matters a lot for high-speed networking. At 10 gigabits, you can get away with a lot of ugly placement. At 400 gigabits, every unnecessary hop becomes a lot more interesting. The same thing applies to storage and GPU direct workloads. When you are trying to move huge amounts of data without bouncing everything through the wrong part of the system, topology is part of the design. PCI Express link state matters too. Do not assume that because a card supports PCI Express Gen 5 by 16 that it is currently running Gen 5 by 16. lspci VV will show both capability and current status. If a high-speed NIC comes up at the wrong width or generation, the interface might still look perfectly normal from Linux. The bottleneck only becomes obvious when you push traffic. This is another place where a known good server is incredibly useful. If two supposedly identical servers produce different topology or link state output, that is worth investigating. And I like to document the expected layout before there is a failure. Which BDF belongs to each ConnectX adapter, which MLX5 device maps to it, which NUMA node owns it, which GPUs are closest. If you only build that map after the cluster is broken, you're doing archaeology while everyone is waiting. There is also a scheduling side to this. Linux has tools like taskset and numactl that let you control CPU and memory placement. Containers and Kubernetes add their own CPU, device, and topology management on top of that. The deeper you go, the more you realize performance is not just about having fast parts. It is about making sure the fast parts are talking to the right fast parts. So if a GPU server works but underperforms, don't immediately assume the application is bad. Look underneath it. Map the PCI Express tree, map the NUMA nodes, check the current link state, compare NIC and GPU locality, and make sure your traffic is not crossing the entire motherboard for no good reason. At this scale, topology is not trivia, it is part of performance.